Hello everyone. In this video, we will continue to examine topic 2.1, and in particular, we will continue to examine the equations of motion for uniform acceleration. All right. So, in the last video, we introduced our four SUVAT equations. We introduced the notation for the 5 variables that are used across 4 equations. All 4 equations relate 4 of those variables to one another. So notice in each equation, one of the variables is left out. And as it turns out, we've actually already seen a couple of them. So I want you to consider a car with a positive initial velocity accelerating at constant acceleration a. Notice this is exactly like our last velocity time graph example. And what we're going to do is we're going to use the velocity time graph to derive the equations, okay, to derive the equations. So in this velocity time graph, I've annotated it here. I want you to pay attention to the red first. The red line here shows our velocity as we increase in IB notation from u, our initial velocity, to v, our final velocity, over a certain amount of time. I'm assuming a positive acceleration here, but you could likewise derive this for a negative acceleration. Notice that the IB variable t is the time interval between the initial time and the final time here. So this is just the variable t. And you can see why that might be confusing, as this t means the time at a particular moment, and this t means the time interval. This is partly, by the way, why I don't like this particular notation. Now, notice that the acceleration is the slope of this line, okay? We know that to be true, and therefore the acceleration is the change in the velocity over the change in time. The change in the velocity in IB notation is v minus u. The change in time in IB notation is just t, and therefore we can derive our very first equation, v equals u plus at. If this looks familiar, this says the final velocity is the initial velocity plus the acceleration times the time interval. That's because it is exactly the equation that we derived way back when we considered this velocity time graph for the first time. And so our first SUVAT equation just is, or stems from, the definition of the acceleration, okay, over this particular time interval. The second equation that we're going to look at is shown in light green here, okay? And it's, well, actually, sorry. We're going to do this blue one first, and then we'll transition to the light green, okay? The blue one is the sort of second SUVAT equation. The green one is the second SUVAT equation. The blue one is the third, but the blue one represents something we've already considered. So I'm going to do blue first. And the thing to recognize is that in IB notation, we know that the displacement is the area under our velocity time graph, okay? So our displacement is the integral of v of t dt. That's just our calculus notation for the same idea. And is therefore the area of this rectangle plus the area of the triangle under the curve. Now notice that in IB notation, the area of this rectangle just is the initial velocity times the time interval, or u times t. Notice that the triangle then has an area of 1/2 base times height, or 1/2 times v minus u, that's the height of this particular triangle, times the time interval t. So 1/2 v minus u times t. And then finally, notice that by equation 1, v minus u is just equal to a times t. So if I rearrange this equation slightly, I get v minus u is equal to a times t. I then plug that into my equation, and that gives me this SUVAT equation, which says that the total displacement is equal to the initial velocity times the time interval, that's this area, plus 1/2 at squared. That is the extra area, okay, in this particular triangle, 1/2 the acceleration times the time interval squared. Notice that this t squared is because as you go higher in time interval, as the time interval increases, you're gaining more and more displacement for every second that passes. That's the significance of the t squared in that equation. And then finally, we can get one more equation by considering the same graph. So the first thing to recognize is that imagine I split v minus u in exactly half. Okay, that quantity is known as the average velocity over that time interval. Notice it is only the average velocity in this time interval because the acceleration is constant. Okay, so the average velocity is going to be halfway between v and u. So I'm going to split that in half, and notice that the area of the underlined green section is exactly equal to the area of the blue section. So the area of the green is exactly equal to the area of the blue. And therefore, that means the total displacement, okay, the total displacement is equal to the area of this green section. As a result, we get this equation, which says that the average velocity is equal to 1/2 v plus u, that's this particular quantity, 1/2 v plus u, notice v plus u, not v minus u. And then that quantity, so 1/2 v plus u times the time is equal to the total displacement, this green area right here. Notice that this is can also be considered as the average velocity, right? The average velocity is the total displacement over the total time, which in IB notation is s divided by t. Okay, and therefore the second equation is s equals v plus u divided by 2 times t. All right, so all of these three equations can be acquired by considering a constantly accelerating object on a velocity time graph, okay, using our graphical techniques.